Hello and welcome everyone. Today in this part of video we are going to discuss about one of the very important theorem of chapter polynomial, and that theorem is remainder theorem. So let's get started everyone. So before we go into deeper part of how remainder theorem can be implemented in our various calculation, first of all let us state what is remainder theorem is. So the remainder theorem can be stated like this: when a polynomial px of degree n is divided by the divisor x minus a, then remainder r will be pa, where the degree of quotient will be n minus 1. Now everyone, first of all let us try to understand what this statement says to us. So let us consider a polynomial px, that means this polynomial it is in the variable of x. So now if we have a polynomial px, maybe fx, kx or ky, there can be various forms of polynomials. So right now let us suppose the polynomial is px and it is of degree n. Now as we know that we have the standard form of the divisor, and whenever we are trying to talk about, or whenever we are going to discuss about remainder theorem or any other kinds of theorem, then we must keep in our mind one thing, that we need such divisors whose degree is 1. So right now we have taken the divisor x minus a. It can also be said as standard form of the divisor in degree 1. So as our polynomial px is in variable x, so I have taken the divisor which is in the standard form as x minus a. So if the polynomial of px having degree n is divided by a divisor of degree 1, then a remainder can be obtained by r equals to pa, where a is any constant term. And as we can see here, when the polynomial of degree n is divided by a divisor of degree 1, then obviously the degree of the quotient will be 1 degree less than that of the polynomial. That means the degree of the quotient will be n minus 1. Now in this case we have discussed about how can we find the divisor for polynomial px when the divisor itself is in the standard form, that is x minus a. But as we know that there are various other forms of the divisor who is also having the degree 1. So let's talk about those divisors and how can we find the remainder, or what will be the value of the remainder in all cases. Now let us discuss degree 1 divisor for polynomial px and their respective remainder values. So as we have discussed earlier also, if we have the divisor x minus a, then as x minus a itself is a standard form or standard divisor form. So in this case the value of the remainder would be r equals to pa. Now let's talk about the second form. The second form of the divisor of degree 1 is x plus a. As we have already discussed that a is any constant term. Okay, so if there is x plus a, or if the divisor is in the form of x plus a, then it can also be stated, or it can also be written in terms of standard form. That means as you can see here, x minus within the bracket minus a. So if we have the divisor x minus x plus a for polynomial px, then the value of remainder would be r equals to p minus a. Now let's go to see the third form of the divisor. If the divisor is in the form of ax minus p, then it can also be written in terms of standard form, that is a common and within the bracket x minus b by a. Now in this case, when the divisor is in the form of ax minus b, then the value of remainder would be p b by a. B is any constant term, whereas a is also any constant term. So after getting the value of p b by a, that last value or the final value that we obtained applying in polynomial px, that will be the actual value of the remainder when the polynomial px is divided by the divisor ax minus b. Now let's talk about the last form of the divisor having degree 1, that is ax plus b. So ax plus b also can be written or can be expressed in a standard form. So in this standard form, as we can see here, in constant part there has come minus b by a. So the remainder value for polynomial px when it is divided by the divisor ax plus b would be r equals to p within the bracket minus b by a. So here we have discussed about 4 different divisors of degree 1, and when these 4 different forms of divisors divides the polynomial px respectively, then we can respectively find their remainder value. Okay, so that's what we have discussed here. Now let's apply our remainder theorem in our few calculations. And how can we find the remainder, or how can we find any unknown coefficient when remainder value is given for any polynomial and for any divisor? So let's talk about some examples. So let's see this question. Find the remainder when 3x cubed minus 5x squared plus 2x minus 3 is divided by divisor x minus 2 with the help of remainder theorem. So here we can see the polynomial expression that we are provided is in variable x. So let us consider it is a polynomial px. Okay, so here we are provided the polynomial px, and also we are provided here divisor dx x minus a. So if we compare this divisor x minus a out of those 4 different types of divisor that we had discussed earlier, then of course, yes, this divisor exactly seems like our standard form of the divisor, which is x minus a itself. So where the value of a would be 2. So comparing our divisor x minus 2 with x minus a, so when we do compare with this one, then value of a would be simply 2. So this value of a is very crucial while we are finding a remainder. So by using remainder theorem, we know that when the remainder that we have to find out, when the divisor is in the form of x minus a, then we know that r equals to pa. That would be the actual form. Right now the value of a is 2, therefore the remainder values would be r equals to p2. So now putting this value of p2 in given polynomial px, so the expression would be like this. So wherever we are seeing the variable x, everywhere I have replaced that value x by 2, because in place of x now we are putting the value of a, that is 2. So first expression, it will be 3 times 2 cube, that means 2 cube is 8, 8 3s are 24. So the first value would be 24 minus 2 square 4, 4 5s are 4 5s are 20 plus 2 2s are 4 minus 3. So these are the terms that we can find. So by using simple operation of Badmash rule, so that means 24 plus the 24 plus 4 would be 28, and minus 20 minus 3 would be 23. So 28 minus 3, that would be simply 5. So now we can conclude that when this polynomial px is divided by the divisor x minus 2, then remainder would be 5. And one very important thing that we have to understand, that remainder theorem can only help us to find out remainder. It can not help us to find out, or it through remainder theorem it is not possible to find out quotient. So let's move ahead. This remainder theorem is sometimes very crucial in some of the calculation. So we'll be talking about that, why remainder theorem is very important in our other examples as well. Now let's see second example. I think we have got some idea from example 1. Now let's go to example number 2. So this question says that using remainder theorem, find the remainder when a polynomial 3x cubed minus 8x squared plus 3x plus 5 is divided by divisor 3x plus 1. So as you can see here, the polynomial is in degree 3, and we have also divisor which is in degree 1, but divisor this time is in the form of Yes, of course, it is in the form of ax plus p. So we know that the divisor which is in the form of ax plus b must be converted into, or must be expressed into, a standard form. Then only we can find the actual value of a. So now here the polynomial px is 3x cube minus 8x square plus 3x plus 5, and we have divisor dx is 3x plus 1. So as you can see here, 3x, from 3x plus 1, let us take out 3 common. So once we take out 3 common, then within the bracket it would be x plus 1 by 3. But we know that the divisor should be expressed in standard form, where in standard form there should be minus symbol or minus sign in between variable and the constant term. So to bring that minus, I have taken minus outside, and to balance this one I have kept minus inside. So when we expand this one, or when we simplify this one, again eventually we can obtain the same divisor, which is 3x plus 1. So now moving ahead, so this time the value of a would be minus 1 by 3. Okay, so now using remainder theorem, we know that by using remainder theorem we have r equals to pa. That's the basic definition that we have obtained from remainder theorem. So r would be equals to pa. So this time, as we know that the value of a is minus 1 by 3, so it would be simply minus 1 by 3, and that is actually expressed in terms of minus b by a also. It can be said like that also. So the value of remainder r equals to p minus 1 by 3. So we have polynomial px, so let's apply p minus 1 by 3 in polynomial px. So when we apply the value of p minus 1 by 3 in px, so wherever x, we can replace it by writing minus 1 by 3. So it's a simple calculation, as you can see here. So it would be simply 3 as it is. There are various ways to calculate this one. So minus 1 by 3 whole cube would be minus 1 by 27. You can understand like this also. And then minus 8 is there. So now within the bracket there is minus 1 by 3 square. So minus square would be plus, obviously. So it will be obtaining only, we can obtain only 1 by 9 plus, and this 3 and this 3 actually can be cancelled. So it would be only minus 1 inside the bracket, so plus 5. So simplifying further, we can see that I have done in another way also, as you can see here. So minus 3 by 27. So I have not cancelled any term, I have just multiplied them. And in the second part there is minus 8 by 9, because minus square would be plus, so outer side minus remains the same one. And then 3 by 3, 3 ones are 3. I have just multiplied the numerator with numerator, but as I said earlier, we can cancel this 3 and 3 also. So it would be minus plus minus outside, and then 3 by 3 plus 5. So moving ahead, we can take 27 as a LCM. So when we take 27 as a LCM and do all the calculation, then our final value of remainder would be 3. So from this calculation we can clearly state that when polynomial px is divided by the divisor 3x plus 1, then the value of the remainder will be 3. I hope the calculation would be so much easy and you will be easily obtaining the value of remainder. So now let's go to our third example, that how we can apply remainder theorem, or why it is somehow essential to find out the remainder theorem. As you can see in this question, find the remainder when polynomial this in variable y is divided by divisor y plus 1. So as you can see here, the polynomial is of degree 100. So now let's think for a while. If we try to find the remainder by using normal division method or synthetic division method for divisor y plus 1, then obviously it will take a lot of time, because the process itself will be so much lengthy, and there is so many process will come, so that it will take more time to find out the value of remainder. But at that time, remainder theorem will play very vital role, which can help us to find out the remainder even in a few steps and within few minutes of time. So due to that reason also, remainder theorem is very much essential. And as I said earlier, this remainder theorem will not help us to find out quotient. So only finding remainder thing can be done through this theorem. So this time, as you can see here, as we can see here, the polynomial is in variable y. So let us say here py polynomial is this: 3y to the power 100 minus 5y to the power 93 plus 2y minus 3, and divisor dy equals to y plus 1, which should be expressed in standard form. So y outside minus and within the bracket minus 1. So when we compare this divisor y minus minus 1 with our standard form, then the value of a would be minus 1. So using remainder theorem, we know that the value of remainder will be r equals to pa. So or pa, this time the value of a is minus 1, so r equals to minus 1. Now we know that we are going to put the value of p minus 1 in polynomial py. So when we put all the values, then it will be like this. So as you can see here, 3 is the coefficient and minus 1 to the power 100, that is, or negative base to the power even would be positive, we know that. So it will come only 1, minus 5 is coefficient in the second part, and minus 1, that is negative base to the power odd, means would finally the value would come negative. So that means the final value would come minus 1, and then plus 2 into minus 1 would be simply minus 2, and the last constant term we can see here 3. So simplifying further, 3 ones are 3, and minus 5 times minus 1 would be plus 5, and minus 2 minus 3 is there. So easily we can cancel this 3 plus 3 and minus 3. So the eventual value of the remainder is 3. So in this way, for such polynomial having so much high degree also can be easily calculated through remainder theorem, and we can get the value of remainder. So in this way we can get the remainder value. So due to this reason also, this remainder theorem is very essential in our polynomial chapter. Now in this three example 1, example 2 and example 3, we have discussed here about how we can find the remainder for a given polynomial when they are divided by their respective divisors. Now let's do some more new thing. That means if remainder are given to us for any divisor to any polynomial, so in that case, if one of the coefficients are missing in case of polynomial, then how can we find such missing coefficients? Now let's discuss about that. So first question is, when a polynomial x cube minus 4x square plus mx plus 11 is divided by divisor x plus 2, then remainder 1 obtained. Find the value of m. So in case of polynomial, let's say px or fx or kx, polynomial in this polynomial px, one of the coefficient is unknown, that is m. It is given us in terms of n. So now our work is to find this value of m, but one more extra information that are given to us, that the value of the remainder when the polynomial is divided by the divisor x plus 2 is 1. So now let's apply remainder theorem and let's get the value of unknown coefficient. So here we have polynomial px is x cube minus 4x square plus mx plus 1, and divisor is x plus 2, which should be expressed in standard form. Yes, obviously it will be x within the x minus within the bracket x minus 2. Good. So when we compare this divisor with our standard form x minus a, then the value of a would be minus 2. That's right, everyone. So as we are given here the value of remainder as a 1, so by using remainder theorem, now we can apply that r equals to p minus 2. That's good, very good. So some alternative case that can be done here. This time we are given the value of remainder, which is 1. So or 1 equals to p minus 2 would be minus 2 cube, as you can see here, minus 2 cube minus 4 into minus 2 square, and plus m remains same coefficient, and times in terms of x there would come minus 2 and plus 11. So these are the things that will comes under first step. Now I can write same or here also in the next step. 1 equals to minus 2 cube would be minus 8, and then minus 4 times minus 2 square, minus 2 square would be 4, 4 for the 16, so 16, and m times minus 2 would be minus 2m and plus 11 as it is. So now let's see all the terms, all the like terms on the RHS part. So when we see all the terms on the RHS part, then there is minus 8, minus 16, plus 11 is there. So when we simplify this all, minus minus would be plus, so it would be minus 24 plus 11 minus twice m. So simplifying further on the RHS part especially, LHS is minus 1, let's keep it as it is. Now it would be minus simply minus 13 minus 2m. So let's send this minus 2m to the left hand side and 1 to the RHS part, then 2m would be equals to minus 11 minus 13 minus 1 by simple calculation, then or the value of 2m would be equals to minus 14. So when minus 14 is divided by 2, the value of m would be minus 7. So in this way we can easily find here the unknown coefficients. So I'd like to show you the steps that the same thing I have done here. So first step, as we discussed earlier, I have just replaced the value of x as a minus 2 everywhere, and then simplifying further, I have got minus 13 minus 2m on the RHS part, and LHS part there is r as a remainder as a 1. So finally the value of m is minus 7. So in this way, in converse way also, it can also be said like that, we can easily find the unknown coefficient. Now let's see one more example so that the idea would be more clear to us. So this example also says that remainder 3 obtained when a polynomial kx cube minus x square minus within the bracket k minus 1x plus 2 is divided by the divisor 2x minus 1. So now the idea is very much similar. Here the polynomial px is given to us, and divisor is given as a 2x minus 1. So we know that it has to be expressed in terms of standard form, which is x minus a form. So when we take out 2 common, then within the bracket we can see x minus a form. So the value of a would be, yes, 1 by 2. Now remainder that we are provided by the question is 3. So using remainder theorem, r equals to p 1 by 2. So applying here also with the same idea, or LHS would be 3, remainder equals to 3 equals to, in polynomial there is coefficient k first. So k, x cube is there, so 1 by 2 whole cube minus, and there is x square is there, so 1 by 2 whole square minus k minus 1 as a coefficient, and x is there, so 1 by 2 plus 2. So moving ahead, LHS, let's keep 2 as it is equals to 3 as it is. So k by 8. I think you are quite clear, that is 1 by 2 cube would be 1 by 8. So when 1 by 8 multiplies with k, it will be k by 8 minus 1 by 2 square would be simply 1 by 4. So minus, let's simplify this one. K minus 1 times numerator 1 of 1 by 2 would be k minus 1 itself. I have not simplified it with further things, by 2 plus 2. Now after getting this one, or 3 equals to if we take out the LCM on the RHS part, the LCM would be 8. So the terms on the numerator of RHS would be k minus, when 4 divided by 2 it would be 2, and 2 times 1 would be 2 ones are 2, minus when 8 LCM is divided by denominator of k minus 1 it would be 4. So that 4 would multiply completely k minus 1, and finally when the denominator 1 of 2 divides the LCM 2, it would be 8 itself, so 8 to the 16. Now calculating further, so when we do cross multiply, then 3 8s are 24 would be there on the LHS part, taking denominator of RHS on the LHS part by doing cross multiplication. So when we simplify the right hand side numerator, then k minus 2 minus 4k, yes, and minus minus would be plus, 4 ones are 4, plus 16 would be there. Now let's simplify further. When you simplify further, then let's keep 24 as it is, equals to, if you see the right hand side, then there are so many like terms. So k and minus 4k is there, so when we simplify it would be minus 3k, good, and there is minus 2 plus 4 plus 16 is there, so 4 plus 16 is 20, 20 minus 2 is plus 18 by simple calculation. Now let's take this 24 and 16 together, 18 together. So 24 minus 18 equals to minus 3 on the RHS part. Now 24 minus 18 is simply 6. So 6 equals to minus 3, we can see here 3k. So eventually the value of k is minus 2. So in this way we can easily find the unknown coefficient or the value of value k. So the same thing I would like to show you through formal process order also. So as you can see here, I have just simplified all the things. I have taken LCM of 8 and I have done cross multiply, and after simplifying the RHS part all, when we simplify all the RHS part, eventually we got the value of k as a minus 2. So with these 5 examples we have discussed here what is remainder theorem and how it can be implemented, or how we can apply this remainder theorem in our various calculation of the polynomial. So now let's talk about some classwork question or some practice question after understanding these all things. So use remainder theorem and find out remainder in each of the following case. So I hope that after learning about remainder theorem and after going through few examples that how we can implement remainder theorem, you can easily find out the remainder in each of these 4 questions. I hope that you all are clear about what is remainder theorem and how it can be implemented in our various calculation. So in this way we have finished our this part of the class. Now in our next class or in our next video we'll be discussing about what is factor theorem and how it can be implemented in our various calculation. Thank you so much. Thank you for being with us. Thank you.